Now, suppose we now wish to find the rate of change of z equal f of x, y at some point in the direction of an arbitrary vector AB. Well, we take the gradient, which is our derivative, and we dot it with a unit vector. The reason you want to be a unit vector, you don't want to change the value, the quantity of the gradient. Unit vector, we know the magnitude of a unit vector is 1, so make sure that's the case. This way, the outcome would be out of z equal f of x, y, and not altered by the length of the vector. So, example 3, find the derivative of f at the given point. We know how that works. The gradient of f is going to be the partial with respect to x, the partial with respect to y, evaluated at 1, 3. The gradient is pretty much 2 minus 3, negative 1, negative 1. Now, if I want to find a unit vector in the direction of 45 degrees, what I'll do, I'll say let u equal, the cosine of 45 degrees is radical 2 over 2, the sine is radical 2 over 2, or 1 over radical 2, whatever you like. I know the magnitude is 1, so all what I have to do is take the directional derivative of u of f of x will be that gradient. So this is in the direction of this vector specifically, will be negative 1, dotted with radical 2 over 2, radical 2 over 2. And in this case, I'll get negative radical 2 over 2 minus radical 2 over 2. And that's, of course, a dot product. It's a scalar. And I'll get this to be negative radical 2. And that would be the rate of change in that direction. I have another example I want to look at. They could also give us an actual vector. Well, the same deal. Find the rate of change at the given point. Rate of change from now on, kind of like me saying find the rate of change or velocity or derivative. That's simply the partial with respect to x, the partial with respect to y, evaluated at negative 1, 1. That would be negative 4, 4. So I got the derivative, so to speak. Now I need the unit vector in this direction. So magnitude of u is actually the square root of 9 plus 16. That's 5. So I'll take the vector to be 3 over 5, 4 over 5. Make sure this is a unit vector. And if I want the directional derivative of f of x, y in the direction of this vector u, I'll simply dot the 2. And later on, we will talk about what this means. And that is negative 12 over 5 plus 16 over 5. That would simply be 4/5. We could apply this, of course, to higher dimension. It doesn't matter. The gradient of f, in this case, partial with respect to x, e to the y. Partial with respect to y, that would be x e to the y. And partial with respect to z, that would be 4z, evaluated at 1, 0, 2. The gradient of f would be e to the 0, 1, 1 times 1, and a 2 in there, that's an 8. And I would have to make the same. I have to take the magnitude of u, that turns out to be the square root of 1 plus 4 plus 4, that happens to be 3. I'm choosing those to be really nice numbers. 1/3, 2/3, 2/3, and if I find the magnitude of this vector, it's a 1. And now I'll say the directional derivative of f in the direction of vector u would be simply 1, 1, 8, dotted with 1/3, 2/3, 2/3, and that would be 1/3 plus 2/3 plus 16/3. and that is all over 3, 16, 18, 19. So the work is not that bad at all. You just need to digest what we're doing. Now, let's talk a bit about how to find the maximum and the minimum in this case. So if I want to find the maximum, I'm taking the gradient, let me choose a darker color. I'm taking the gradient of f dotted with u. Isn't that by definition the magnitude of f, the magnitude of u, times the cosine of theta? Remember that? Given that assume that's the gradient of f, which is a vector. Assume that's a unit vector right there, u, and the angle between them, then that formula holds, right? And if I look at this, I'm looking for the rate of the directional derivative of x, y, which equal the magnitude of f. Magnitude of the unit vector is 1 times the cosine of theta. And this right here is really this right here. So pretty much what I conclude out of this, the directional derivative will be a maximum. The rate of change will be a maximum if theta equals 0. What does that mean? That means this vector right here lines up with the gradient. That would be the maximum. I'll simply get the magnitude of f. That will be the maximum. The minimum change will be when theta equal pi, meaning I'll get the opposite direction. And I'll get this to be 0 or non-existing if theta is pi over 2. If the unit vector happen to be perpendicular to the gradient, then you're going to get the actual rate to be 0. So the maximum, if I really want to sum this, the maximum rate of change of the gradient of f is in the direction is in the same direction as the unit vector, and the minimum or the smallest rate of change of the gradient is in the opposite direction. That's really what I'm getting out of those, as u is. Now, that's how we find a maximum or a minimum. If I take the next problem, and I'm looking now for a maximum, I'm looking for a few things. I want to digest what this means, not only for this section, for the coming sections. Find the direction in which the function increases and decreases more rapidly. I'll find the gradient of f, the partial with respect to x, that's y, plus, and here I'll get e to the xy times y, the sine of y. Partial with respect to x, with respect to y, that will be x, and here I need the product rule. Derivative of the first is going to be e to the xy times x, the sine of y, plus e to the xy times the cosine of y. If I evaluate that at the point 1, 0, my gradient function is going to be 0 for y, and 0 right there, that will make that a 0. And here I'll get 1 plus e to the 0 is 1 times x, which is a 1, sine of, that's a 0, plus, and if I put that here, that's a 1, cosine of 0 is a 1. So I'm getting the gradient of f to equal 0, if I'm not mistaken, 2. So, in this case, I would say the maximum rate of change, or let me go differently, f increases most rapidly F increases most rapidly in the direction of 0, 1. Any multiple of that will do, but we like to keep it as a unit. You don't have to, but that's better for most of what we do. And it decreases most rapidly in the direction of negative 0, 1. And if I look for the actual maximum rate, that's the directional derivative of f evaluated at p sub 0. That's del f dotted with u again. That is the magnitude of f, because the magnitude of u is a 1. And in this case, that would be the square root of 0 plus 4, which is 2. That would be the most, and the minimum would be a negative 2. That's simple. Now I could do this on higher dimension as well. That works the same way. The same deal. The work is almost identical. I'll take the gradient of f of this 4 dimensions. That would be partial with respect to x, that is y e to the x. Partial with respect to y, that's e to the x. Partial with respect to z, evaluated at natural log of 3, 1, 2. The gradient of f would be natural log of 3 for x, that's a 3 times 1. That is a 3, and that's a 4. Again, if I'm not mistaken. So I got the gradient to be 3, 3, and a 4. That's the key. Now out of this, I can make my conclusions. If I look for the magnitude of, that would be the square root of 9 plus 9 plus 16. That's the square root, and I need that number for 18, but 34. I'll save that. But for now, if I want to talk about the direction of this, f increases most rapidly in direction of 3 over radical 34, 3 over radical 34, 4 over radical 34. Okay, I don't like that. That's kind of squished in here. 3 over radical 34, 3 over radical 34, and 3 over radical 34. And f decreases most rapidly in the direction of negative 3 over radical 34, 3 over radical 34, and 4 over radical 34. Oh, I put a 3 there. There. And the maximum out of this, the maximum rate would be actually radical 34, and the minimum rate would be negative radical 34. Now, given a 3-dimensional surface, let's say I'm given a surface that looks like this, and I have some curve C. If I take a point on it, some P0, and I draw a tangent plane that touches at one point, R prime will point in the direction of C, the gradient of f will be perpendicular to that. So if the gradient is perpendicular to my tangent, then I'm going to assume that's really A, B, C from our chapter 12. And given that point, I could figure out the tangent line, and I could figure out the normal line, and I could figure out the equation of the plane as well. So there is a big theorem in the book that explains that. I explained that at the very beginning. First problem, I'm gonna sort of explain this with a sketch. Let me get the equation up. So if I have the function being given, and again it has to be f of xy equals c for the gradient to work, that's important. So here I want to sketch the graph of the circle. Well, that's easy to do. With a radius of 5, let's assume this is a 5. So sketch the graph of x squared plus y squared equals 25 together with the tangent line. How am I going to sketch the tangent line? At the point 3, so 3, 4, somewhere like right there, I need to find an equation of a tangent line. I not find the equation of a tangent line by taking a derivative, but here things are slightly different. What I want you to remember is the sphere and the tangent plane. Remember the sphere that I showed you? If I'm thinking of this as a sphere in 3 dimensions, and this instead of this tangent, instead of a line being a plane, then I'll take the gradient of f, which is 2x, 2y, evaluated at 3, 4. That would be 6, 8. So if I take this, the equivalent of my normal vector, do you remember that? Again, it's not, but let's say that's what I'm assuming it is. So this is like my AB, and if I take A into x minus 3 plus 8 into y minus 4 equal 0, I'll get 6x minus 18 plus 8y minus 32 equals 0, or 6x plus 8y equals 50, or simply 3x plus 4y equals 25. Now why would that work? Because I know the normal vector 6 to the right, 8 up is going to be perpendicular to the plane, and this is going to be perpendicular to the tangent as well. Now I went on Dismos and I sketched a graph of, and you can see it, it's right there on the left, and let me show. I sketched x squared plus y squared equal 25, that's the red graph, and 3x plus 4y equal 25, and this is what I got. The normal will be pointing upwards. So this is one easy way to figure out the equation of a normal line. You use this like you used V. It's perpendicular to the plane, and therefore it's perpendicular to the line as well, and that should give you the equation for the plane in 3 dimensions and the line in 2 dimensions. That was the first video. That was what it was all about. And if I take the following, if I have a 3D, I know what that look like. Find an equation of the tangent. So there's the tangent line. That's the equation for it. Now find the equation of the tangent plane. Well, the deal is, again, you must have f of xy on one side, everything else on the other side, for this gradient to work the way you want. It has to be in that form. So I need the vector. The point is there. I know it's going to be the equation for a tangent plane is going to simply be a into x minus 1 plus b into y minus 2 plus z into plus c into z minus 4 equals 0, just like we did this. And where am I going to get A, B, and C? That's going to be the gradient, because it's going to be normal or perpendicular to this plane. So partial with respect to x, 2x. With respect to y, with respect to z, evaluated at 1, 2, 4. The gradient is going to be a -2, a 4, and a 1. So now I could say, find an equation of the tangent plane that is -2 into x minus 1 plus 4 into y minus 2 plus 1 into z minus 4 equal to 0, or -2x plus 4y plus z, that's a +2, minus 8, that's -6. -6 minus 4 is a -10. Set that equal to the right, and there's my tangent plane. And if I want a normal line, x equal the 1 plus a -2t, y equals a 2 plus 4t, and z equal a 4 plus t. That would be the equation of a normal line. And I'm going to graph that and show you that in a minute. I was trying to graph it and it didn't match, which means I made a mistake, and I see where the mistake is. It's right there. If I take the partial with respect to x, it's -2x. That should have been a minus when I move this to the left. So this is -2y and a 1. And if I substitute 1, that's a -2, that's a -4. So that will change few of those. That will make this a -4. And that will be -2x minus 4y plus z equaling. That's a +2. 2 plus 8 is 10. 10 minus 4 is 6. When I move that to the other side, that's a -6. So let me see what happens when I graph this. And let's see that really quick. So let me see what I have to fix here. X equal 1 minus 2. So this should be a -4t, and everything else is fine. So if I go to GeoGebra, and if I sketch the graph, and let me show you the equations right there. If I sketch the graph of z equal x squared plus y squared minus 1, it's right there. If I put the point 1, 2, 4, the point is on it right there. And if I sketch -2x minus 4y plus z equal -6, there's the tangent plane. And I could even sketch the vector -2, -4, 1. Let me see how to do that. Do I know how to do that? -4, actually, I don't know how to do that yet. Oh boy, that's not going to work. Okay, I don't know how to sketch a vector yet. I'll figure that out. But if you graph it, it's going to be pretty much perpendicular. And that would be it for this section. Now in the next section, we're going to play more with tangent planes, a lot more than this. This is just like an introduction. And that concludes this section. Quickly, find the maximum rate of change.